Hello, dear students. Welcome back to our discussion on refrigeration and air conditioning. Now, in our present lecture, let us discuss a new topic, that is air refrigeration system. Air refrigeration system, or it is having another name, that is reversed Joule cycle. It can be considered as a reversed Joule cycle. And the Joule cycle you might have learned in your previous sessions, in your junior classes. Then it is also called as Bell-Coleman cycle, named after the scientist who proposed this idea. Okay, so as the name suggests, air refrigeration system. Air refrigeration system means it is the air itself is the working fluid, or the working fluid which is capturing heat from the cold space and rejecting the heat to a high temperature space, etc., etc., are the same and one and only our air. The atmospheric air is considered as the working fluid which is carrying out all the work in the refrigerator. That is, the air will be taking up heat from the cold space, for example, the freezer compartment of our household refrigerator, and it will be rejecting the heat to the surroundings, which is at a higher temperature. So, what is this air refrigeration system, or why it is considered as a separate cycle? The modification of the ideal reverse Carnot cycle resulted in this cycle. Why we had to modify the, or why we had to think beyond the Carnot cycle? Carnot cycle itself is a ideal. It is only a ideal cycle. It is only a benchmark for discussing other ideas in refrigeration. Why? Because in the Carnot cycle, we are having two isothermal process or constant temperature process. Okay, which will be that is, if we are practically implementing a constant temperature process, it will be very slow process. Then the other two processes in the Carnot cycle are reversible adiabatic process or isentropy process, which if practically implemented would have to be completed very fast. That is, alternate isothermal and isentropy processes are occurring in a Carnot cycle, which means isentropic, that means alternatively very slow processes and very fast processes have to be implemented if we are going for implementation of Carnot cycle, which is practically impossible. That is, implementing a very slow process, suddenly switching over to a very fast process like isentropy process, then again switching back to a very slow process like isothermal process, again switching back to a very high speed isentropy process, like that it will be, that is, our entire machine will be having a very large amount of wear and tear, and it will be very difficult to control that machine. So instead of thinking about this ideal Carnot cycle, so we are modifying this Carnot cycle and thinking whether we can modify this Carnot cycle and use that whether we can modify the reverse Carnot cycle and whether we can use it for refrigeration. So this idea was put forward by Bell Coleman, and the air refrigeration system came into existence. That is, what was the modification suggested by the scientist? The isothermal processes, which are normally the time-consuming processes, which they were replaced using constant pressure process. So, in a real-life situation, achieving a constant pressure process is not that a big deal. Okay, we can almost achieve almost nearly 90% of a constant pressure process. Okay, so the constant pressure processes replaced the isothermal processes in a reverse Carnot cycle. So let us see how it was implemented in a air refrigeration system. So this is a diagrammatic representation of a air refrigeration system. So in the last, I think in the first classes, I told you, that is, we mechanical engineers, usually when we are going to discuss a new concept, we will be first representing it on a piece of paper, or we will be first trying to diagrammatically represent the entire system. Okay, so then after representing this the new system on a piece of paper or on a computer screen like this diagrammatic representation, we will try to represent this diagrammatic representation in some meaningful representation like a PV diagram or a TS diagram or any thermodynamic diagram like that in the case of refrigeration system. So this is the diagrammatic representation of a air refrigeration system or reversed Joule cycle or Bell-Coleman cycle. All the three words are same, conveying the same meaning. So here you can see the prime important part of the refrigerator is nothing but our the cold space or the freezer compartment, or where we want to create a very cold temperature. We are calling it as the refrigerator uh, component, okay, or the refrigerator part. So here the refrigerator part is marked between 4 and 1, this space. Okay, this space can be assumed as the freezer compartment of our household refrigerator. Okay, so from this refrigerator or the cold temperature space, the air, which is the working fluid, it will be absorbing heat from this refrigerator part using constant pressure process. Okay, in a constant pressure process, then that air will be admitted inside the compressor. Okay, the compressor is assumed as a piston cylinder arrangement. Okay, for representation sake. Okay, actually a compressor may or may not be a piston cylinder arrangement, but for representation purpose we are assuming the compressor to be a piston cylinder arrangement as shown here. Okay, that piston and the connecting rod is attached to a shaft which is rotated by an electric motor. Okay, then this compressor will be compressing our working fluid, which is nothing but the air. The after compression, this air, it will be admitted to a heat exchanger. Okay, a heat exchanger portion where the air, our working fluid, it will be rejecting the heat to a coolant medium. Okay, there will be a provision for coolant in and coolant out. There will be a coolant continuously circulated throughout this heat exchanger. This coolant will be absorbing heat from our working fluid, that is air. Okay, so you can so if you observe here, the heat will be absorbed by the working fluid, that is air, from the refrigerator. Okay, then it will be at a low energy. Okay, it will be at a low energy. Then that working fluid, that is air, it will be compressed by our compressor using isentropic compression. Okay, the compressor work and the expander work are remaining same as the Carnot cycle. There is isentropic compression process and isentropic expansion process. Okay, so the compressor will be isentropically compressing the our working fluid, that is air. So due to that compression process, the temperature of our working fluid, it will be increased. The both the energy and temperature of the working fluid, that is air, it will be increased. And it is that high temperature, high energy air or the working fluid which is entering the heat exchanger. So this working fluid, that is air, it can easily reject that high energy or high temperature energy to the down to the coolant medium which is circulated throughout the heat exchanger. Okay, so after rejecting the heat to the rejecting that extra energy or heat to the coolant medium, the air or the working fluid, it will be coming out of the heat exchanger. It will be admitted inside the expander cylinder. Okay, actually the expander cylinder also, here it is assumed as a piston cylinder arrangement for representation purpose only. But in our actual modern day refrigerator, we may not find a expansion device in the form of a expansion cylinder. Instead of a piston cylinder arrangement, it can be a simple one-way valve or a throttling valve, which will serve the purpose of the expansion. But here, for representation purpose only, we are assuming the this expander working also as a piston cylinder arrangement. The piston will be attached to the connecting rod, which will be attached to a moving shaft, which will be again actuated by the same electric motor. Okay, so it is this electric motor which will be consuming the electric power, and that will be the main electrical power consumption of our refrigerator. Then after this working fluid is expanded inside the expander, its volume will increase. Its volume will be slightly increasing. At the same time, the temperature will be brought down to a very low temperature. Actually, it will be brought down to a very low temperature or lower than that of the refrigerator. Again, it will be admitted to the refrigerator. Since the air is having, since the air is now having a lower temperature than the refrigerator space, again after admitting it to the refrigerator, it can again absorb heat from the refrigerator. It will be again admitted to the compressor, and the cycle will continue like that. Okay, so this is the diagrammatic representation of our air refrigeration system, or reversed Joule cycle. So now let us try to represent this. Now let us try to represent this in a meaningful thermodynamic diagram. So now let us take the help of PV diagram, and now let us try to represent this air refrigeration system in a PV diagram and TS diagram. Okay, so now let us focus on the compressor work. Okay, how this compressor work is happening. So our working fluid, which is nothing but the air, it will be absorbing heat from the cold room, that is the refrigerator, at a constant pressure. Okay, at a constant pressure. Then it will be that air, after absorbing heat from the cold room at a constant pressure, it will be admitted inside the compressor. So as we have discussed, compressor is assumed as a piston cylinder arrangement. Okay, so we know the piston cylinder arrangement, it will be having a suction stroke, then it will be having a compression. During the suction stroke, the piston will be moving away from the top dead center. It will be moving down to the bottom dead center. During that suction stroke, the air will be admitted inside the compressor cylinder. So here that suction stroke, it is represented as 4 dash to 1. So the suction stroke of the compressor is represented as 4 dash to 1. So here we are not seeing any point like 4 dash. 4 dash is nothing but a imaginary point. Okay, 4 dash is nothing but some imaginary point which is occurring at the which is occurring between this exit of the refrigerator and the entry of the compressor. Okay, somewhere in this line, some imaginary point we are considering, that is 4 dash. Okay, so from that 4 dash to 1, the suction stroke is happening. So during the suction stroke, air from the refrigerator, during this suction stroke 4 dash to 1, air from the refrigerator is drawn inside or into the compressor cylinder during the suction stroke. The suction stroke is represented as 4 dash to 1. Then uh, then comes the compression stroke of the compressor. Okay, so during the compression stroke, the the piston will be moving from the bottom dead center. It will be moving upwards towards the top dead center, compressing the air inside it. Okay, so we are assuming it this compression process as isentropic compression process. So that isentropic compression process, it is represented using the line 1 to 2. It is represented using the curve 1 to 2 here. Okay, so compression is happening from 1 to 2. So we know during the compression process what will be happening to the volume of the air or the working fluid. It will be getting reduced. Okay, the volume of the working fluid will be compressed, or the volume will be getting reduced inside the compressor. So that is represented as here 1 to 2, the volume is getting reduced. But what will happen to the temperature? Temperature will be increasing. Okay, we know the PVT relationship, P1 PV by T is a constant. We know the basic thermodynamic relation, PVT relationship. So when the um, volume is getting reduced, the volume is getting reduced, and the pressure is increasing, the temperature will also increase. Okay, so the temperature, so if we are representing it in a TS diagram, 1 to 2 process will be isentropic process. At the same time, the temperature will be increasing. So that is why temperature is increasing from 1 to 2. So 1 to 2 is represented like this in a vertical line, like this in TS diagram. Okay. Then after this compression process, there will be the delivery stroke. Uh, the delivery stroke of the compressor cylinder. During the delivery stroke of the compressor cylinder, the this delivery valve will be opened from the compressor cylinder. The compressed air will be moving out. It will be let out towards the heat exchanger, and that is represented as 2 to 3 dash. 2 to 3 dash. 2 is the end point of the compression stroke, and the delivery stroke is represented as 2 to 3 dash. So this warm air, it will be admitted towards the it will be admitted towards the heat exchanger in that stroke. So here also a point like this 3 dash is represented here in this diagram, but we are not seeing any point like that in the cycle. Actually 3 dash can be assumed as a imaginary point somewhere here. That is, after immediately after the compression stroke, it will be the air will be moving towards the heat exchanger. In between this line, somewhere in this line, we can assume a point like this 3 dash. So 2 to 3 dash is the exhaust stroke, sorry, the delivery stroke of the compression cylinder. So in that in that delivery stroke, the warm air compressed by the compressor, it will be moving towards the heat exchanger. So after getting inside the heat exchanger, what is happening? This warm air, which was compressed by the compressor, it will be rejecting the heat towards the coolant medium. Okay, it will be rejecting the heat towards the coolant medium. That heat rejection process is occurring in a constant pressure process, or during that heat rejection, the temperature of the air will be getting reduced. Okay, so in this TS diagram, it can be represented like this: from 2 to 3. 2 to 3 is the heat rejection process happening inside the heat exchanger. The heat from the warm air is rejected to the coolant medium, so the temperature is getting reduced. So this curve is a constant pressure line. Okay, so this constant pressure line can be represented as the heat exchanger pressure line. That is, what is the pressure maintained at this heat exchanger? It will be a constant pressure line. It will be constant pressure, and that pressure can be represented as the line 2 to 3. Okay, during that heat exchanger process, or the heat rejection process, the temperature of the working fluid will be getting reduced from 2 to 3. So during this process, the what will be happening to the volume of the working fluid? It will be getting, it will also be getting reduced. So again, recalling our PVT relationship, here it is a constant pressure process, so P is a constant. So volume is sorry, the temperature is getting reduced, so the volume also will be getting reduced. Okay, from 2 to 3. So actually during the delivery stroke of the compressor, the air is moving from 2 to 3 dash. Then comes but how this point 3 is coming, let us discuss. So now we are over with this compressor work and the heat exchanger work. Then the warm air, after rejecting the heat to the coolant medium, it will be losing out much of its energy, but it will be still at a high pressure. Okay, even though the temperature was brought down, even though the temperature was brought down, the pressure is remaining same. It will be at a higher pressure due to the compressor working from 1 to 2. Okay, even after heat rejection during the heat exchanger, the our working fluid is still at a very high pressure. In With that high pressure, if we are admitting our working fluid direct to the refrigerator part may burst or it may tear out. The side walls of our freezer compartment may tear out due to that high pressure. Okay, so we have to bring down that high pressure of the working fluid using some expansion device. Okay, then only it can be admitted back to our refrigerator. So in that consideration, we are fitting a expander cylinder between the mm, um, exit of the heat exchanger and the entry point of the refrigerator. So in order to bring down that high pressure of the working fluid, it will be admitted to inside of a expander cylinder. So now let us consider the working of a expander cylinder cylinder arrangement. So this expander operation is represented in this third diagram over here, in the PV diagram over here. So please observe. So, um, so the warm air, after rejecting the heat to the coolant medium, it is coming out of the heat exchanger. It will be at a very high pressure, as we have discussed here. It will be at a very high pressure. So some imaginary point 3 dash can be assumed somewhere between the exit of the heat exchanger and the entry of the expander. Okay, so 3 dash can be assumed. Since it is an imaginary point, it can be assumed anywhere before or after the heat exchanger. So when we are considering the expander process, we are assuming that imaginary point after the heat exchanger. Okay, so from that imaginary point 3 dash to 3, the inlet stroke or the suction stroke of the expander cylinder is happening. So the expander cylinder, the piston, it will be moving from the top dead center towards the bottom dead center. That will be the inlet stroke or the suction stroke. So during that suction stroke, the warm air, the air, the working fluid, after rejecting the heat to the coolant medium inside the heat exchanger, it will be admitted to the inside of the expander cylinder, and that is represented as 3 dash to 3, the inlet stroke, the suction stroke of the expander cylinder. Then immediately after entering the expander cylinder, just like our compressor cylinder, the power stroke or the working stroke of the expander will be happening. That is, the expansion process will be happening. The expansion process is assumed as a isentropic expansion process. So it is represented as a curve in a PV diagram, 3 to 4, 3 to 4. So it is a expansion process. Isentropic expansion process means no heat is lost or gained by the system or the working fluid. So the 3 to 4, the temperature will be brought down, but it will be a constant entropy process or isentropic process. So 3 to 4, or the expander working, is represented as a vertical line in a TS diagram like this, and 3 to 4 it will be represented as a curve in the PV diagram. Then just like our compressor working, the piston cylinder arrangement of the expander, it will be opening the delivery valve. Then the delivery stroke of the expander will be resultant, it will be occurring, and that is represented as 4 to 4 dash. 4 to 4 dash is the delivery stroke of our expander cylinder. So 4 dash is nothing but some imaginary point in and around this refrigerator compartment. Okay, so 4 to 4 dash. Okay, so that is the expander cylinder working. So combining this expander cylinder working and the compressor cylinder working, if we combine both this compressor cylinder operation and expander cylinder operation, our Bell-Coleman cycle, or the reversed Joule cycle, or the cyclic representation of air refrigeration system can be obtained like this. Okay, so the air refrigeration system or the reversed Joule cycle or the Bell-Coleman cycle can be represented in the PV diagram like this: 4 to 1. That is the heat absorption process from the refrigerator happening at a constant pressure process. Then 1 to 2, that is isentropic compression process happening inside the compressor. Then 2 to 3, then 2 to 3, 2 to 3 is the constant pressure heat rejection process happening inside the heat exchanger. The heat is getting rejected to the coolant medium at a constant pressure. Then 3 to 4 is our expander cylinder operation. 3 to 4 is again happening isentropically inside the expansion cylinder. Okay, then the cyclic represent this that will be the cyclic representation of this air refrigeration system in a PV diagram. The TS diagram representation will be like this. Okay, 4 to 1. 4 to 1 is the constant pressure heat absorption from the refrigerator component by the working fluid, that is air. 4 to 1. Then 1 to 2 is the isentropic compression process happening inside the compressor. Then 2 to 3 is the constant pressure heat rejection process happening inside the heat exchanger. And 3 to 4 is again the opposite of the compression process, that is isentropic expansion process. 3 to 4 is coming like this. So this is the PV diagram representation, and this will be the TS diagram representation. Then now the next step in our analysis will be trying to find out the COP, or coefficient of performance of our air refrigeration system. Okay, so now let us try to find out the coefficient of performance. How the COP is defined? It is the refrigeration effect divided by the net work done. Okay, the refrigeration effect, what is the refrigeration effect? The refrigeration effect is nothing but the heat absorbed from the refrigerator, the heat absorbed from the cold space. It is happening during the process 4 to 1, and at the same time it is a constant pressure heat absorption process. The temperature will be increasing, but it is happening at a constant pressure. So that is why CP, that is specific heat constant at a constant pressure. CP, P stands for constant pressure. CP times the temperature change. The temperature of the working fluid, that is air, it is increasing from 4 to 1. The temperature of the working fluid is increasing from T4 to T1. So that temperature change, Cp times delta T, is the refrigeration effect produced by the working fluid. Actually, the representation should be mCp delta T, but for calculation purpose, we are taking the mass flow rate of the working fluid as 1, or unity. Okay, then the denominator is the net work done. Net work done will be nothing but the heat rejected minus heat absorbed. The heat is getting absorbed by the working fluid during 4 to 1. The heat is rejected by the working fluid, that is air, during 2 to 3. Okay, so again 2 to 3 is a constant pressure process. It is the temperature of the working fluid, that is air, is decreasing from T2 to T3. So T2 to T3, the temperature is getting reduced. So the heat getting rejected is nothing but Cp times T2 minus T3. So substituting all these, that is Cp into T, that is heat rejected is nothing but Cp times T2 minus T3, and the heat absorbed is nothing but the refrigeration effect produced, that is Cp into T1 minus T4. Substituting all these in this COP relation like this, and cancelling out, we can cancel out the common Cp terms. Okay, then the resulting expression will be like this: 1 by T2 minus T3 by T1 minus T4, the whole minus 1. Okay, so this is the this is one result that we are getting today, that is the COP of the air refrigeration system. 1 by T2 minus T3 by T1 minus T4 minus 1. But this, as you know, this is having this is a almost a complex relationship relation that is containing some T2, T3, T1, T4. That is almost four variables. Actually, suppose we can reduce the complexity, or we can arrive at a simple relation. Okay, a simpler relation. That is our aim. Okay, we are going to modify this complex relation that we will be discussing later. Okay, thank you for today.